If we magnified the scale of our planet, we would see more than just continents. We would see the indelible mark of a civilization that chose to defy all limits. Here, steel soars among the clouds, water flows backward, and a giant eye scrutinizes the silence of the cosmos. These are works that no longer belong to engineering, but to legend. Prepare for a journey where the impossible becomes concrete, steel, and data. The 11 megaprojects of China that forever redefined what humankind is capable of building. The bridge over the void, when the ground doesn't exist. In the heart of Yunnan province, nature sculpted a barrier that for millennia was an endpoint. The Jinsha River Grand Canyon is not simply a valley, it is a gaping wound in the Earth's crust, with vertical walls plunging more than half a kilometer to a raging river below. For the communities on either side, crossing meant a grueling and perilous descent on dirt roads, a river crossing, and an equally arduous climb on the other side. A 4-hour journey to cover as the crow flies, a distance a bird could traverse in seconds. The geography here didn't suggest a bridge. It forbade it. There was no stable bedrock on which to drive the pillars, only the dense air and the abyss. Conventional engineering yielded to this landscape, but 21st century China did not. Its response was not to seek more forgiving terrain, but to completely redefine the concept of a bridge. The Jinsha Grand Canyon Bridge is a structure born from the denial of the ground. With a roadway suspended 625 meters above the river, a height surpassing that of the Shanghai Tower, this colossus of steel and concrete has been, since its opening, the tallest bridge on the planet. Its construction was an act of extreme balance and precision. Unable to raise towers from the canyon floor, all the work was carried out from the edges of the cliff. Steel beams weighing thousands of tons were assembled in mid-air, extending from each bank until they met in the center of the void with a tolerance of millimeters. Rockets were used to launch the initial guide cables across the abyss, the train that crosses the text of the world. If the Jinsha Bridge defies the vertical void, another project faces the most extreme horizontal hostility on the planet. The route between Chengdu in Sichuan province and Lhasa, in the Tibet Autonomous Region, is widely considered the most formidable railway engineering challenge ever undertaken. This is not just terrain, it is a geological battlefield. The line traverses the active collision of the Indo-Australian and Eurasian plates in the Hengduan Mountains, one of the most violent seismic zones on Earth. Here, earthquakes are frequent, massive landslides are commonplace, and the elevation jumps from 500 meters to over 4,000 meters, crossing permafrost regions and mountain passes where oxygen levels can drop to as low as 40%. Breathing here is difficult. Building a railway with millimeter precision was, for many, a suicidal fantasy. The Sichuan-Tibet Railway is the embodiment of that fantasy. With a total projected length of over 1,600 kilometers, its most complex section, the one linking Ya'an to Ningqi, is a marvel of engineering and survival. In this segment, more than 90% of the track doesn't touch the ground in the conventional way. The train doesn't snake along hillsides, it literally drills through and leaps across the landscape. It's an endless succession of deep tunnels, some at altitudes of over 3,000 meters, piercing unstable mountains and spectacular bridges, like the one spanning the Dadu River, which overcome gorges several hundred meters deep. Engineers have had to develop special concretes that cure in low oxygen environments, ventilation and oxygenation systems for the tunnels and stations, and anchoring techniques for constantly shifting slopes. The cost, both financial and human, has been monumental, and the project has required decades of planning and execution. But the reward justifies it all. The 55-kilometer Dragon, a science fiction solution. While mountains were being conquered in the west, a diametrically opposed challenge faced in the south. The sea. Specifically, the Pearl River estuary, one of the most congested waterways on the planet, with thousands of merchant ships, tankers and ferries crossing its waters every day. Connecting the prosperous metropolises of Hong Kong, Zhuhai and Macau with a road was an obvious economic dream, but a perverse engineering puzzle. A continuous 55-kilometer bridge would block maritime traffic, strangling the very economy it was meant to unite. An underwater tunnel of that length was technically unfeasible and astronomically expensive. The question seemed to have no solution. How to cross a sea without disrupting the sea? The answer didn't come from a single type of structure, but from a combination that borders on science fiction. The Kong-Zhuhai-Macau Bridge is a hybrid transportation system, a steel and concrete dragon that snakes, plunges and emerges above the water. This 55-kilometer colossus is neither a bridge nor a tunnel. It is both at once. It begins with cable-stayed bridge sections that rise above secondary navigation areas. Then, to allow the passage of large container ships and tankers, it plunges into the depths. The crown jewel is its 6.7-kilometer submerged underwater tunnel, the longest in the world, built in the open sea. This tunnel was not excavated but constructed using the submerged tube method. 33 reinforced concrete segments, each the size of an aircraft carrier and weighing 80,000 tons, were fabricated on land, towed to the precise location, and meticulously sunk to be joined together on the seabed. The tunnel emerges at 2 artificial islands, monumental land reclamation projects that serve as a transition between the underwater and above-ground worlds. The invented river. Correcting a geographical error. Sometimes the greatest obstacle to development is not a mountain or a sea, but a quirk of hydrology. In the Guangxi region of southwest China, a cruel geographical irony exists. It is a coastal province bordered by the Gulf of Tonkin, and yet its main rivers, the Xiang and the Li, do not flow into the sea at their feet. Instead, they take an absurd turn and travel hundreds of kilometers north to join the Yangtze River, forcing any cargo destined for the sea to make a monumental detour through other provinces. For centuries, this error of natural drainage stifled the economic potential of a resource-rich region, increasing transportation costs and isolating its industries. The solution, once again, was monumentally audacious. If the rivers didn't flow to the sea, a new one would be dug that would. The Pingloo Canal is, quite literally, an invented river. At 135 kilometers long, it is the first large-scale artificial navigable canal built since the founding of modern China. The scale of the excavation is difficult to grasp. The total volume of earth and rock moved exceeds 700 million cubic meters, enough to fill the Three Gorges Dam 3 times over. It is a surgical cut through the landscape, directly linking the Pearl River system to the sea. With an estimated investment of over 9.4 billion euros and a completion date set for 2026, the canal will allow the passage of ships up to 5,000 tons. This will shorten the distance to the sea for inland goods by 560 kilometers, saving time and fuel and resulting in over 600 million euros annually in avoided transportation costs. The beast of the Ginga River, taming hydraulic fury. While bridges and canals connect, there exists another kind of giant whose purpose is to transform the raw power of nature into the constant pulse of civilization. Energy. And in the turbulent upper reaches of the Ginga River, a tributary of the Yangtze, stands one of the most perfect and terrifying machines ever built, the Baihetan Hydroelectric Dam. The chosen site was not the most convenient, but rather the most powerful and challenging. This region, on the edge of the Tibetan Plateau, is a nightmarish geological laboratory. Fractured terrain, constant seismic activity, and the erosive force of a river that sweeps away mountains. To build a structure here that had to contain a reservoir of billions of cubic meters of water and withstand colossal hydraulic pressures was, in essence, a challenge to the physics of materials. The answer was a masterpiece of precision engineering, a double-curved arch dam, a 289-meter-high concrete vault that, like a colossal bow, transmits the monstrous thrust of the water to the canyon's rock walls. Every concrete pour was monitored with sensors to control the temperature and prevent cracking, a process of obsessive meticulousness. But Baihetan's true marvel is not its exterior, but its beating heart. In its powerhouse, buried in the rock, lie the largest and most powerful hydroelectric turbines on the planet. 16 units, each with a capacity of 1 million kilowatts. Highways of light, teleporting electricity. Generating clean, abundant energy in remote locations is only half the battle. The other half, perhaps more complex, is getting it to where it's needed. China faced a continent-wide energy dilemma. Its greatest renewable energy resources, the relentless winds of Xinjiang and Gansu, the scorching sun of the Gobi Desert, the hydroelectric power of the far west, were trapped 2,000 or 3,000 kilometers from the electricity-starved coastal megacities and industrial centers of the east. Transporting this energy with conventional transmission technology at voltages of 500 or 750 kilovolts would have been an exercise in frustration. Resistance losses in the cables over such distances would have dissipated a huge portion of the electricity before it reached its destination. It was like trying to send pressurized water through a long, porous hose. The solution was to invent a new hose, one so efficient that it would practically teleport the energy. Thus was born the ultra-high voltage transmission network, the nation's invisible electrical backbone. UHV is not a simple upgrade, it's a quantum leap. These lines operate at voltages of 800,000 and even 1.1 million volts, the highest ever used commercially in the world. At this stratospheric voltage, less current flows to carry the same power, drastically reducing heat losses. It's the equivalent of turning a bumpy dirt road into an 8-lane highway for electrons. Building this network was a feat in itself. It required the development of gigantic transformers, insulators capable of withstanding enormous mechanical and electrical stresses, and transmission towers that rise like skyscrapers laid sideways, crossing deserts, mountains, and rivers in runs of more than 3,000 kilometers. The cumulative investment amounts to tens of billions of euros. Its impact, however, is transformative. The river that flows backwards, a civilization's life support system. If energy is the pulse, water is the blood. And here, China faced its most existential paradox. The distribution of its water resources is a cruel, inverted reflection of its demographic and economic distribution. The south, particularly the Yangtze River basin, receives abundant monsoon rains, is prone to catastrophic flooding, and its rivers carry colossal volumes of water. The north, on the other hand, home to the political capital Beijing, the megacity of Tianjin, and essential breadbaskets for the nation's food supply, is arid and thirsty. Its underground aquifers were overexploited for decades, sinking to critical levels. Water scarcity threatened not only growth, but the very survival of hundreds of millions of people and the stability of the economy. The solution was a project that belongs to the realm of classical epic, forcing water to flow uphill, through mountains and under rivers, against its natural course. The South-North Water Transfer Project is, without exaggeration, the largest hydrological intervention in human history. It is not a single project, but a system of 3 massive routes, east, central and west, that together will move tens of billions of cubic meters of water annually from the Yangtze River basin and its tributaries to the northern plains. Its central route, already completed and operational, is an engineering marvel. It stretches for more than 1,200 kilometers, from the Danjiangkou Reservoir to Beijing and Tianjin. To achieve this, the water doesn't just travel through open canals. It performs incredible feats. It cuts through mountains via deep tunnels, and in its most symbolic feat, passes beneath the mighty Yellow River through an inverted siphon, a tunnel that runs deep under the riverbed. The scale is difficult to grasp. As of 2024, this system had transferred more than 70 billion cubic meters of water to the north. To put it in perspective, that's enough water to completely fill the Dead Sea. More than 150 million people already depend on this continental water source for their drinking water, industry and agriculture. Without this transfer, cities like Beijing would have imposed severe water rationing years ago. The magnet that bends. Reality, the invisible border. Beyond dams, power grids and aqueducts, there exists a category of megaproject that isn't measured in kilometers or megawatts, but in its capacity to manipulate the fundamental forces of the universe. This is the realm of extreme science, and its temple in China is the Hefe High Magnetic Field Laboratory in Anhui province. At first glance, it lacks the majesty of a suspension bridge or the intimidating scale of a dam. It's a complex of research buildings, but inside, it houses a machine that represents the absolute frontier of precision engineering and experimental physics. The most powerful and stable hybrid magnet in the world. Its purpose isn't to generate energy or transport water, but to create a patch of space with conditions that don't exist anywhere else on Earth. The laboratory's central achievement is generating a continuous magnetic field of 45.2 Teslas. The field created in Hefe is hundreds of thousands of times stronger. At this level, magnetism ceases to be a passive force and becomes a tool that literally bends reality, distorting the properties of materials and allowing the observation of otherwise invisible quantum phenomena. Achieving this is not a matter of building something large, but of controlling something extreme. The hybrid magnet is, in itself, an engineering feat of overwhelming complexity. It combines an enormous external superconducting magnet, which operates at temperatures near absolute zero, requiring a massive cryogenic system with liquid helium, with an internal copper resistance magnet. The latter is the true challenge. When operating at full power, the electric current passing through it is so colossal, tens of thousands of amperes, that it dissipates an amount of heat equivalent to that of a small nuclear reactor. The cooling system that prevents the magnet itself from melting is a monumental feat, using deionized water under pressure circulating at incredible speeds. The installation consumes, in its brief peak operating times, as much energy as a small city, energy that must be supplied in a stabilized and instantaneous manner. The impact of this machine is profound and silent. It is a fundamental tool for cutting-edge research. Scientists from around the world use this ultra-strong magnetic field to study the structure of new materials, develop high-temperature superconductors that could revolutionize energy distribution, test drugs at the molecular level, and unravel the secrets of condensed matter physics. The Steel Star, where immenseness meets efficiency. A country projecting itself as a global power requires a gateway commensurate with its scale and aspirations. At the beginning of the 21st century, Beijing faced a crisis of success. Its capital's airport, already expanded for the 2008 Olympic Games, was saturated. Its airspace and runways were operating at their limits, stifling growth. The solution could not be a simple expansion. It had to be a complete redefinition of what an airport hub means. Thus, Daxing International Airport was born, a steel and glass behemoth that resolves the paradox of massiveness with geometric elegance. With an investment of over $11 billion and built in just 5 years, Daxing rises south of the capital like a gigantic golden starfish. It is the largest single-building terminal on the planet, with an area under one roof exceeding 1.4 million square meters, capable of handling 100 million passengers a year. Daxing's genius, however, lies not in its size, but in how it negates the distances that size normally imposes. Its radial design, with a large central core and 5 arms extending toward the boarding gates, is a masterstroke of efficiency. Any traveler, regardless of which arm their flight is in, can walk from the center of the terminal to the furthest gate in a maximum of 8 minutes. This logistical feat is achieved through a perfect choreography of smart technology, facial recognition systems for seamless flow, robots that assist with baggage, and seamless integration with ground transportation, including a high-speed train that connects directly to downtown Beijing. The Ghost Port, when robots rule global trade. If Daxing is China's air gateway, its maritime gateway faced an even more fundamental challenge. Shanghai, perched on the Yangtze Delta, saw its status as a river port become a disadvantage. The latest generation of mega container ships, with drafts of more than 15 meters, could not approach its docks. The conventional solution would have been to continuously dredge the riverbed, a losing battle and ecologically costly. China, once again, opted for the radical solution. If the ships couldn't reach the port would go to the ships. Thus, the Yangshan Deepwater Port was conceived, a project that literally involved moving the port infrastructure to the open sea. To do this, it was first necessary to build a connection, the 32.5-kilometer Donghai Bridge, one of the longest over the sea. At the end of this bridge, on the Yangshan Islands, a colossal land reclamation project was undertaken, reclaiming space from the sea for container terminals. Phase 4 of this project is the heart of the future, the world's largest fully automated container terminal. Here, operations are a spectacle of silence and robotic precision. Giant gantry cranes controlled by algorithms unload containers from ships without a human operator on board. Automated guided vehicles resembling large rolling platforms, move autonomously around the container yard, coordinated by an artificial intelligence system that optimizes every movement to minimize waiting times. The Eye of the Sky, a monument to human curiosity. After connecting continents, mastering rivers, and automating trade, one final, pure, and selfless ambition remains: to understand our place in the cosmos. This ambition took concrete form in the remote karst mountains of Guizhou province. Here, far from the electromagnetic pollution of cities, stands the 500-meter aperture spherical radio telescope known as FAST. Its objective was not economic or logistical, it was scientific and philosophical. The construction challenge was unique: how to support a radio receiving dish half a kilometer in diameter, the size of 30 football fields, with the millimeter precision necessary to capture extremely faint radio signals from distant galaxies. The solution was as ingenious as it was simple: to use a natural depression in the karst landscape as a support. Over this natural basin, engineers constructed a grid of more than 4,500 triangular aluminum panels, each independently adjustable by actuators. This makes FAST an active telescope. Its surface can deform to create an effective parabola in different directions, allowing it to point at regions of the sky, even though the main dish is fixed. Its sensitivity is astounding. FAST is so powerful that it could detect the faint signal of an ordinary cell phone transmitting from the surface of the Moon. Since it began operations, its scientific output has been revolutionary. It has discovered more than 900 new pulsars, neutron stars that spin at incredible speeds, more than all other telescopes in the world combined in the previous 50 years. It scrutinizes clouds of neutral hydrogen to understand the structure of the Milky Way, and participates in the search for possible signals of extraterrestrial intelligence. With a relatively modest investment of around $170 million, FAST doesn't move goods or transport passengers. Its product is pure knowledge. It is a monument to human curiosity, a giant eye wide open to the universe, reminding us that our greatest ambitions are sometimes not to transform the Earth, but to listen, with infinite patience, to the whisper of the stars. These 10 projects, from the bridge that soars over the abyss to the eye that scrutinizes the cosmos, are more than just a compilation of engineering records. Which of these works represents the ultimate achievement, the pinnacle of this will to build? The answer lies not in the data, but in the admiration it inspires. The debate, like the next project already on some drawing board, has only just begun.